Dear students, myself Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Basava Kalyan. Now in the 43rd session of Graph Theory 2, the topic of this session is four color problem and recapitulation of dual of a graph. So now we are at the final stage of this colorability topic. So that is the application part of the colorability. Okay. So already in the introductory part I have given you the idea what is called a coloring of a graph, coloring of a map. Okay. What do you mean by coloring of a map? So coloring any map, it may be Indian map or it may be American map or it may be African continent map, whatever may be the, even it may be a world map. So our aim is to color the map in such a way that if you consider a map of a country, the condition is that no two neighboring or you can say the states with a common boundary have the same color, because if the two states which are having a common boundary, so those states are called adjacent states. So the states which are having a common boundary are called adjacent states. If we color with the same color, you cannot identify. So for that reason, the adjacent countries or the adjacent states must have different color. So that is the coloring of a map. Okay. If I consider the African continent, so there are 53 countries. So now if I ask you to color the map of African continent, so how many colors we require to color in such a way that you can identify all the countries very easily. So one may say that we require 53 colors, or one may say that no, we require less than 53. So like that, so how many colors we require? Oh, overall, so that we are going to discuss in this session. Okay, so that is four color problem. What is the four color problem? Just now I have told you, consider a map. A map, what do you mean by a map? So map means the faces. You will see the faces. Each face represent a state or you can say a country. Okay. So overall conclusion is that if I consider a planar graph, okay, if I ask you to embed that planar graph in the plane, so you will get a plane graph. So in the plane graph, you will get the faces. Okay, interior faces and one exterior face will be there. So overall conclusion is that a map is a plane graph. Of course, it is a planar graph embedded in the plane. A map is a plane graph with states corresponding to faces. Very interesting. A map is a plane graph with states corresponding to the faces. We should be able to color the faces of a plane graph in such a way that the adjacent faces, there I said adjacent countries, or you can say the countries with a common boundary. So instead of that I am using a graph theoretic word. So in such a way that adjacent faces, that is faces sharing a common line, must receive different colors. That is the idea of a coloring. Okay. So now how to color a map? So first of all you have to consider the plane graph of the map. That is, let G be a plane graph, and what is the G star? You know the dual of a graph. So in detail already we have discussed about the dual of a graph, that is the geometrical dual of a graph. So in the plane graph you are considering the faces, some interior faces along with one exterior face. So now our aim is to color the map. It implies our aim is to color the faces of the plane graph. So each face is replaced by a vertex. What I am going to say is that in each face you have to insert one vertex. Okay, and join those two vertices corresponding to the faces if they are having a common boundary, or you can say there is a line, the faces sharing a common line. It implies you cannot assign same color to those two adjacent vertices, because you have to assign different colors to distinguish the faces. So for that reason what we are going to do, so in each face we are introducing a vertex, and if two faces are sharing a common boundary or common line, we join those two. It implies you are finding a geometrical dual of the plane graph. So I said in the planarity chapter, so how the planarity or the planar graphs are useful in the coloring topic. Okay, so let G be a plane graph and G star be its dual. The phase coloring of G, is equivalent to the vertex coloring of G star. So that is very interesting. So if you color the geometrical dual of a graph, so whatever the color you are getting for the vertices, in which the adjacent vertices are having with different colors. So after coloring that dual of a graph, so the same color if you use the corresponding faces, so that is nothing but the coloring of the plane graph. It implies you are coloring a map of any country or any state. Okay. So now let us consider one idea. So what is the definition of n region colorable? So in coloring also I said m colorable. So there we took one graph which is 8 coloring graph. 8 coloring graph is nothing but we are using 8 colors. The same 8 coloring graph we have colored with 6 colors also. So we said it is 6 colorable graph, though it is 8 coloring graph, but it is possible to reduce the colors by 6. So then you can say it is 6 colorable graph. Even if it is possible to reduce by 4, reduce by 3. So suppose if it is reduced by 3 in such a way that you have colored the graph, considering that idea, the adjacent vertices are having different colors. Okay, so that you have to remember always. So if you are able to color the graph in such a way that the adjacent vertices are having the different colors, if with 3 colors if it is possible, then you can say it is 3 colorable graph. Okay, like that n region colorable graph. What do you mean by n region colorable graph? Region, that is the faces. Okay, so it implies a plane graph G is said to be n region colorable if the region of G can be regions of G. Actually, I should use the word the regions of G can be colored with n or fewer colors. As I said, colorable. Though it is 8 coloring graph, you can use 6 colors, you can use 4 colors, colorable. So with n or fewer colors, so that adjacent regions are colored differently. So if it is possible, then you can say it is n region colorable, like m colorable graph. The same concept. Okay. So now we will see what is the 4 color problem. What is the 4 color problem? Okay. So it's very simple idea. The 4 color problem is the problem of determining whether every plane graph is 4 region colorable. You consider any plane graph. Okay, is it possible to color that plane graph with at most 4 colors? So that is the 4 color problem. So the 4 color problem is the problem of determining whether every plane graph is 4 region colorable. For example, if you consider this as a graph, so how many regions are there in this plane graph? R1, R2, R3 are the interior regions. You can say regions or you can say faces. So 3 interior faces, 1 exterior face, that is R4. Okay. So our aim is to color the faces or the regions of this graph. For example, okay. Now you can see R1 and R2 are having a common boundary line, or you can say a common line sharing these two regions, R1 and R2. Okay. You can see properly. Yes. Okay. So R1 and R2 are having a common boundary line or sharing a common line. It implies the vertices in the dual of a graph representing R1 and R2. You have to join those two. You have to join those two because there is a common line. Once if you join those two are the adjacent vertices. So adjacent vertices must have different colors. It implies the vertex coloring of its dual is nothing but the coloring of the plane graph. So once if you color the dual of a graph, considering that idea, so you can color the plane graph. So R1 and R2 must be with different colors. You can very easily identify the faces. Similarly, if I consider the faces R2 and R3, again R2 and R3 are having a common line sharing between these two regions or faces. So it implies again you cannot assign the same colors for R2 and R3. So we need to join these two vertices in the dual of a graph. In G star you are joining these two. So R2 and R3 are adjacent vertices in dual of a graph. So there you have to assign different colors. Okay. So this is how these two faces are also having different colors. But how about R1 and R3? If I consider R1 and R3, is there any common line sharing between R1 and R3? No, there is no any line sharing between R1 and R3. It implies you can assign the color, same color for R1 and R3. So they come in the color classes. R1 and R3 will be in the same color class. Okay, with the same color. Say suppose if you are using blue color for R1, you can use the same blue color for R3 also, because there is no common line or boundary between R1 and R3. So now you can think of the fourth face, that is exterior face, outside. Okay, so there R1 you use and R2, R3, all the faces, interior faces are having a common boundary with R4. R1 is also having common boundary, at least one edge. If it is common, then you can say it is common boundary. There is a common boundary between R1 and R2. Similarly, R2 and R4 also having a common boundary. Similarly, R3 and R4 also having common boundary. It implies, so you cannot assign any color which you use for R1, R2, R3. Okay, so you need to assign a different color. Okay, for R4, because R4 is adjacent with R1, R2, R3. Okay, so therefore you have to assign a different color for R4. So this is the four color problem. So once again, let me recall, the four color problem is the problem of determining whether every plane graph is four reason colorable. So this is the statement of four color problem. Now how to construct a geometrical dual, that already we have discussed in detail, but again we need to recapitulate, because we need dual of a graph, because the face coloring of plane graph is nothing but the vertex coloring of its dual. Okay, so as I said already, the construction of a geometrical dual, what you will do for a given plane graph G, its geometrical dual G star is constructed as follows. Place a vertex in each region of G, including the exterior region. So in each face of a plane graph, you have to insert one vertex. Okay, then what you have to do? And if two regions have an edge E in common, join the corresponding vertices of, or you can say join the corresponding vertices by an edge E star. If E is an edge joining those two faces or common boundary, so E star will be an edge joining those two vertices. Okay, or you can say you have to take one edge crossing the common boundary line. Okay, so in that way also it is possible to construct. So therefore, join the corresponding vertices by an edge E star crossing only the edge E. In addition, one loop is added to a vertex of G star for each bridge of G. So if there is a bridge in the graph G, instead of that bridge, what you have to do? You have to add one loop for that region where you are getting that bridge. Obviously, bridge will be on the exterior face. So for the vertex representing the exterior face, you have to form, or you have to add one loop for the vertex representing the exterior face. Okay, for each bridge of G which belongs to the boundary of the region. Usually exterior region, even you can take in the interior region also, doesn't matter. So this is one example how to construct the geometrical dual of the graph. See, so this is one graph G, the edges are E1, E2, E3, E4. Okay, now how many faces are there in this graph? There are two faces. One is a face containing E1, E2, E3 edges, that is the interior face, and outside one face, that is exterior face. Only two faces are there. So therefore what we did, we have inserted one vertex corresponding to the interior face, and we have inserted one vertex corresponding to the exterior face. Okay, now E1 is a common boundary edge between the face, interior face as well as exterior face. So therefore you have to take one edge E1 star, E1 star joining or crossing the edge E1. It implies we have joined the vertex which is interior to the region and one vertex corresponding to the exterior region by the edge E1 star. Similarly, the edge E2 is a common edge between the interior face as well as the exterior face. So there must be one edge crossing E2, okay, joining again those two vertices. Similarly, E3 is also a common edge. So again we have joined those two vertices by an edge E3 star. Okay, then E4 is a bridge. E4 is a bridge and it is on the boundary of the exterior region. So therefore, a vertex corresponding to the exterior region, we have added one loop. So therefore, the dashed lines with the vertices, two vertices. So this is the dual of a graph G, of a plane graph G. Okay, so I have taken separately from that. So while constructing, just you have to introduce one vertex interior faces as well as one vertex corresponding to the exterior face. Okay, so this is the way to construct the geometrical dual of a graph. Okay, so now what do you mean by underlying graph? After finding the dual of a graph, okay, now you have to see whether there are multiple edges. If there are multiple edges, instead of multiple edges, take only one edge between the vertices. And if there are loops, so neglect the loops or delete the loops. So whatever the graph we are getting, that graph will be the underlying graph of the dual of G star. So, dual G star. Okay. For example, you can consider here, if each set of multiple edges of G star is replaced by a single edge and all loops are deleted, the resulting graph H is called the underlying graph of the G star. For example, if you consider the same example which we have considered, this is the geometrical dual of the plane graph G. Okay. Now between two vertices, how many edges are there? Three edges are joined between the two vertices. It implies if two or more than two edges are joined between the same two vertices, such edges are called multiple edges. So instead of those multiple edges, it may be two, it may be three, or it may be any number of edges joining between two vertices. So what you have to do, instead of the multiple edges, it may be any number of multiple edges, you take only one edge between those two vertices. Okay, so there are three multiple edges. Instead of that, we have considered only one edge, and all loops are deleted. So whatever the graph we get, that will be the underlying graph of the G star. So here H is the underlying graph of the G star. Okay, I hope you have followed easily, because this concept we require for coloring the map or the planar graph. Some observations what we heard in the previous session while discussing the construction of a dual. If G has a bridge, instead of bridge what we are doing in G star, then G star has a loop, definitely. If G has a loop, then G star has a bridge. Okay, though we have not considered the example particularly this, but if G has a loop, then G star has a bridge. If two regions of G have at least two edges in common, then G star has multiple edges. Obviously, in the previous example, we come to know that three edges were common between the interior as well as the exterior face. That's why we got three multiple edges between those two vertices. So, the fourth one, the number of edges constituting the boundary of a region in G is equal to the degree of the corresponding vertex in G star. It's very obvious. So see, one vertex of degree 3, isn't it? Because of three edges were on the boundary of the exterior region. Next, the graph G star is also embedded in the plane. Definitely G star is also a planar graph or plane graph. Okay. Of course, planar graph embedded in the plane is called a plane graph. The graph G star is also embedded in the plane, and hence it is planar. Definitely, it is very obvious. Next, the seventh observation is, considering the process of constructing a dual G star, then the geometrical dual G star from G, it is clear that G is a dual of G star. G is a dual of G star. So that's why we have proved one result. The G star whole star is equal to G. That is, the dual of a dual of the graph is again the graph G. Okay, so these are the observations how we have constructed the geometrical dual of a graph. So overall, what we have discussed in this session. So what is the four color problem? That is a map. Map is nothing but it is a plane graph. Plane graph we are going to color. We are actually our aim is to color the map. So instead of map, we have considered the plane graph. So coloring the plane graph is nothing but coloring the vertices of its dual. So that's why we have discussed what is the four color problem. What is the four color problem? So it is possible to color the map within four colors. So it is four region colorable. Four region colorable. Maximum four colors are sufficient to color the faces of any plane graph. Okay. Then we have recapitulated the concept of dual of a graph. So to clarify the concept, we took some examples. Okay. So with this, we conclude. So these are the references. If you want, you can refer any of the books. So with this, we conclude today's session. Thank you.